In any case, I'm happy to discuss this new paper. Actually, I'm going to go through some old stuff in order to reach to the final stages of what we have done with some collaborators, master students from Sapienza, Alejandro Cardenas Avendaños from Los Alamos, and Paulo Pani. So, yeah, there's I'm lagging. For those that were here last time, you're gonna see maybe 3 or 4 recurring slides that I had the other time also. So here is what I have seen once in my telescope without the black hole, of course, the center of Milky Way. So I went very high up in a mountain where the luminosity of the the surroundings was pretty decent. No moon in the sky, no nothing. I didn't take this picture, of course. I'm just saying that it was really beautiful. You can actually see the Milky Way. And Milky Way comes from the Greek word, which is galaxias. It's not the way, it's the axis of milk. It's exactly what it means in Greek. It's amazing. But here, some artists, I guess, or physicists, put 2 black holes that look like they interact with each other. They're spinning, there's some frame dragging around them. So what will happen is that eventually they're gonna crash on top of each other and form a final object, as we know. And I have this very simple slide which separates the 3 stages of an inspiral of a binary system of compact objects. Right? They can be anything, can be neutron star, black hole, and combination of those may be an exotic object that we don't know. Here, let's assume that we have some amplitude that we are measuring. Here is time, and at the inspiral stage, these 2 black holes, what they do, they accelerate in the gravitational field that they have created. And as they accelerate, they emit energy. They emit gravitational waves. And through the loss of energy, because the system is dissipative, it's closing in, and we have orbits that are closer, smaller and smaller in diameter, because this is a circular inspiral, until we reach the final point of the merger, where the amplitude has increased to its maximum. The black holes collide. This is of order 10 to the minus 21, but still we have detectors that can see that. I will show you. You have seen, but anyway. And then we have some damped sinusoids, which is called the ring down stage, where the final object emits its last, let's say, radiation through the so-called quasi-normal modes, or basically the excitations of the final object. So it goes down back to the lowest energy state. Now, what I want to focus on is on this side, but first let me go through real quick what happened in 2015 and published in 2017. It was a black hole of 2 massive, it was an inspiral of 2 massive black holes that merged, formed all the phases as we saw them before, inspiral, merger, ring down, and it was detected with 2 different gravitational wave detectors that work with lasers, but I don't want to go too deep into that. Now, what we have is 4 detectors. LIGO has these 2 in Washington and Louisiana. Virgo is in Pisa, and Kagra is in Kamioka in Japan. We are currently at the 4 observation run. Okay, so we have increased a lot the sensitivity, the accuracy, any problems that might arise in that analysis. There has been a huge amount of progress. But still, the sensitivity of the detector with all the noise that we create around it, is around the kilohertz band, as you see here in this spectrogram. So we see that the gravitational wave starts gaining amplitude, as we see here, until it chirps, as we say. We call this final stage the chirp. That's after the ring down, the amplitude disappears.
Sorry, but this is the frequency or the amplitude?
This is frequency over
And
time,
and
the color map is yeah, it's a color map and it's a normalized amplitude.
Yeah.
So we have more than 200 detections of black hole binaries, neutron star binaries, black hole and neutron star binaries, some confusing mergers that we don't know where they come from because they are in the mass gap that you cannot have a neutron star because it's unstable. You cannot have a black hole because it's unstable. So this is where all this exotic compact object research is focusing on in these mass gap events. And now, as we see, the mass gap is somewhere down here on the regime where it might be a black hole or a neutron star. And there's also another unstable region up here. We have you see the difference in solar masses is large. So a lot of people play around with this kind of exotic objects that may merge and give some extra information that we can understand that something else is going on besides pure GR.
You mentioned that black holes have stability.
That there's a mechanism here, like it's called a mass gap, that we cannot have a formation of a black hole.
Okay, so for the
or a neutron star. It's another mass gap instability that I'm not very familiar with it. I actually forgot the name. It has a specific name, if anybody remembers, for the large masses. But I really, yeah, I don't remember right now, but I can tell you later. So what I want to focus is on the asymmetric events, because we see some black holes that are usually close to each other, like they have similar masses, and then they give a new one. But for example, I think the one that I'm interested in is this one here, because we have a black hole that is around 8 solar masses that merges with something that is around 30, which is the most asymmetric we can get with LIGO because of the noise pattern of the detector. So we are looking at this system. It's in the LIGO band. This is the 8 solar mass black hole. This is the 30 solar mass black hole. And what if we take this to the extreme limit? Then we have extreme mass ratio. Extreme mass ratio is basically a supermassive black hole with a companion that is of stellar mass. And the supermassive object is called the primary, the secondary, and the stellar mass companion is called the secondary of the system. So this is a binary still, but at the extreme mass ratio limit. These originate in dense stellar clusters and especially in galactic nuclei, in galactic cores, because we have seen that supermassive black holes lurk in these very cryptic spots of the universe in the center of galaxies. And we have pictures of that with the Event Horizon telescope. So we are certain that there's something very massive there. The mass ratio, like to call something an extreme mass ratio in spiral an EMRI, we have to have a mass ratio that ranges from 10 to the minus 7 to 10 to the minus 4. This allows us to do perturbation theory and to also do other interesting things with these objects. Because of the very massive object, the gravitational waves generated here are in the millihertz band. So LIGO, Virgo, Kagra, they are blind to these events if they exist. So what we have to do is try to find another way to probe these binaries and see if they exist and what information they will give us. because the frequency range is very small, then we know that we understand that the secondary will revolve around the primary slowly, very slowly actually. The less massive it is and the more massive the primary is, the larger is its period of revolution. So we expect 10 to the 4, 10 to the 5 revolution in the strong field regime. What the secondary is doing is basically tracing the space-time of the primary. So we can test general relativity with these objects beyond what we have done already, like with much more accuracy, precision, see other effects. And I'm gonna talk, there's a rich waveform phenomenology, but I am interested more in resonances, as you saw in the title. But real quick, this is what we call a space-borne detector. It will go to space, it will avoid all the noise and all the scales that we have on our planet. 2.5 million kilometers between each spacecraft that send lasers to each other with test masses inside made out of some gold something alloy. Whenever a gravitational wave passes, it's like having 2 detectors in space because we have 3 spacecrafts that form 2 arms of the detector. It's going to be some degrees before the sun, so it's going to be in 1 astronomical unit away from the sun, and it will follow the Earth in a particular trajectory, and it will also have its own orbit so that it stays in a, let's say, stable orbit for years with tiny corrections. So this is going to be launched on 2035. It actually got adopted by the European Space Agency, and it got funded by the European Space Agency. A lot of countries are contributing to the construction of the spacecrafts and to the launch of the spacecrafts. NASA is also contributing in other ways. So it's a very nice, detector that we're gonna have. I mean, we're not gonna have data in 10 years. In 10 years, it's gonna be launched. And if it's set up right, then we have to wait some years. There's a lot of sources that fall in the millihertz band. So it's gonna be very hard for data analysts, but it's gonna be very nice when we get clean data from data analysts as physicists, as theoretical physicists. And just to mention and advertise a little bit my country, we also play an active role in the theoretical part of the LISA consortium. We have done recently a whole conference about it, and we're planning to do this like every couple of years or so to enter more in depth into the LISA consortium. Okay, so I saw this last time in the group meeting, but I was much faster. Now I will try to be a little bit more thorough about how we model these EMRIs, because we need models that gives us very accurate waveforms that keep the phase correct. If we lose the phase and compare with some data that we receive, then we will not get what we want. We ruin signal to noise ratio, we get weird parameter estimation and stuff like that. So let's assume at first, at short time scales, at some orbits around this object, that we have geodesics. It's the easiest, it's a 0 order approximation of this extreme mass ratio binary. It's not inspiral yet, it's just a geodesic. And I assume a stationary and symmetric spacetime, any spacetime, I'm not putting it down to some specific one, that has this GTC term in the metric tensor so that we have rotation. So we're trying to do some, to find an astrophysical, to have an astrophysical primary. From the geodesic equations, we get 4 second order coupled differential equations, and from Euler-Lagrange equations, which we know that they are equivalent to geodesics in a curved spacetime, we can find that through stationarity, we have a conserved energy, which is written with respect to the metric tensor components and P dot and phi dot. You see that we already took out one derivative from both T and Phi, and Phi comes from axis symmetry, which gives us the constant Lz. So if you rearrange these two, you can write T with respect to just the metric tensor components that we have here and the constants of motion, nothing else. And they are not P dot, of course, and then you solve it. So it's a first order differential equation that is not coupled with the rest of the system. What is coupled now is only R and theta. R and theta are still second order and coupled. We have the conservation of rest mass in the beginning that gives us this constraint here. R prime are the four velocities, theta prime, again, for velocity, for the polar motion, and we have an effective potential that appears. So if we take the conservation of rest mass, which practically the conservation of the Lagrangian or the Hamiltonian or all these things that are equivalent with each other, then we get this. And this potential defines the region outside the primary that we have bound geodesic motion. Bound means that if we start with appropriate initial conditions that are defined by this constraint, then we will stay in there forever if we do geodesics. If we add dissipation, then this region shrinks because energy, Lz, they change and they become smaller with respect to time. So if we put V equals 0, so we want this constraint to be satisfied, okay? So for this to be 0, all this equation, we have to put the effective potential equals 0, because the other thing that we can do for this to be satisfied is R dot is 0, theta dot is 0, and the effective potential is 0. Everything is positive here squared, so they have to be 0. What R dot and theta dot equals 0 means? It means that we have turning points of the orbit. And we can see this in phase space. But remember the curve of zero velocity and the bound motion in the R theta plane. Now, if we're lucky and this space-time has another constant of motion, then we have integrability. And in Kerr, for example, there's the Carter constant, which is not a killing vector, but a two-rank killing tensor. And this separates the radial and the polar motion in the same way we have separated these two. And then we have four separated ordinary differential equations of first order to solve separately, so much faster. By the way, this Carter constant can exist like in other spacetimes that are generalizations of Kerr. It's not the Carter constant exactly, it's Carter-like. It has some extra terms in it. And again, we have integrability. So we can have integrability even beyond GR as long as we have something that is 2-rank or 4-rank or something of higher order killing tensor. But this is what we know for Kerr. Now, if we don't have this extra constant, then we have non-integrability, and this means chaos. But I'm not going to go to chaos yet. If I have time, I will discuss just a little bit. Now, I'm going to go a little bit deeper in the perturbative scheme that we should use and to get accurate waveforms. For long time scales, we have to include effects of dissipation, losing energy, shrinking of the orbit, so an inspiral. The best method till now is gravitational self-force to do that. Imagine that it's the equivalent of black hole spectroscopy for bring-down analysis. This is the best thing we have right now. I don't know if it will change, but it makes sense. It just takes a lot of time and you will understand why. We start with the secondary, and we do not assume that it is a test particle, so it doesn't follow geodesics per se, but it has some acceleration, which creates a back reaction to itself and gives it a self-acceleration to the secondary. It's the same as a radiation reaction. It's the same process. So we can expand the four acceleration in leading order self-acceleration, second order, third order, and so on. Eta is the mass ratio and is the small number, 10 to the minus 7, 10 to the minus 4. So going beyond eta squared is redundant. I mean, it's useless because the contribution will be very, very, very small. Now, when we have integrability, the good thing that we can do to understand the phase and the shape of the orbit is to transform the Boyer-Lindquist coordinates to the action angle variables, as we call them. Action is for the shape, angle is for the phase. And this is, I mean, there are a lot of discussions about self-force and how to put it together. These two are some very nice reviews about gravitational self-force in general relativity. But these two equations define how the angle and the action parts of the orbit evolve with respect to all these combinations of equations. Now, up here we have the fundamental frequencies of geodesics, okay? Zero order expansion. The first order in mass ratio, we have this G, this small g, which essentially includes dissipative terms, loss of energy. To second order, the second order dissipative term, and then here we have this capital G that gives us shift to the orbital frequencies and second order and so on and so forth. So including the action variables that describe the shape and the angle variables that describe the phase, we can understand through this set of equations how energy is lost from the system in first and second order, and zero order, of course, which is geodesic, and also how the shape of the orbit changed. The shape has to do with, of course, what I'm going to talk about, which is the resonances. So for now, to make you understand how difficult this is to work with, we have to first order in gravitational self-force. So these terms only, and these, of course, for curved geodesics, which are generic, inclined, and non-equatorial, inclined, eccentric, which is called the generic orbit, to first order in Kerr. And to second order, we have it only for Schwarzschild. For Kerr, second order is to include these terms here also, we don't have it yet, which are the post adiabatic terms that include more resonant effects and also spin, the spin of the secondary and so on and so forth. If we manage to reach here with Kerr to eta squared, then we are done for Kerr EMRIs, of course. If you want to do this for a modified theory of gravity, good luck. This took 10 years and we still don't have it fully developed. I'm not working on that, but people, Adam Pound, Van der Met, Waddell, Lynch, Upton.
I think modified effects they would enter their effect on the waveform stronger than the effect from second order.
You know, why is that?
I mean, I guess in many cases, like for example, if the scalar fields, there is a dipole contribution that is entering equated zero.
Okay,
It's like dominating and you don't need to compute.
I think the point is different. That for LISA, we need very precise waveforms to perform the data analysis. So I mean, you need it in every order.
No.
Oh, yeah, but
You
what
don't
I mean
need
is
it to
like,
every order.
No, I mean,
This is impossible.
I mean, like, if you have like the curve for second order to compare, you need the modified gravity also to second order. So
Yeah, but there are lots of modified gravity theories, right? I mean, they don't always appear on the third order in mass ratio or something. You also have astrophysical environments, accretion disks, etc., like active galactic nuclei, dark matter halos, and so on and so forth. So these terms may appear here. In general, this is a theory-dependent task, and it's extremely hard. That's how I understand this problem, and that's why I want to do simplifications and approximations to solve this, because I don't know how to do this with pure gravitational substance. So this is EMRI modeling made easier. So we take the adiabatic approximation. We know that the phases of the orbit change slowly, so we can do this expansion, where the red part is the dissipative first order cell force. The blue part is the part that represents corrections due to orbital resonances. So we affect small g, we affect the capital G, and so on and so forth. The green part, which is in eta 0, the 0 order, denotes post-adiabatic effects. Okay, so this is a way that you can start to simplify your problem. And to simplify, I'm going to take out this, and every other thing. And I'm going to keep only the dissipative first order cell force, which means I only care about loss of energy to see how the inspiral evolves. I don't really care about the shape, but this affects, of course, the phase, because they're coupled equations. And the adiabatic approximation basically truncates derivatives of the action angle variables to eta, drops the forcing term, this one, because it oscillates rapidly, and replace this term from the previous equation with its time average. And this is what we call the fluxes of radiation, depending on the system, the flux of energy, of Lz, of the Carter constant, if we have a curved spacetime. So now what we do is, besides the adiabatic approximation, which simplifies the problem a lot, this is still a hard problem to solve. It really is. So we use the numerical class, which has been it started back in early 2000 by Gaer and Glabedakis, and it has been used to compare waveforms with Tecnico-based evolutions. And what we do here is that we approximate this flux with post-Newtonian formula. We go up to second post-Newtonian order, and we stop there. So it's an approximation on top of an approximation on top of an approximation. But this gives us this beautiful sentence here. The inspiral flows through successively damped geodesics. So we can assume that this, which corresponds to either the flux of energy, Lz or Q, evolves linearly, and then with a recurring loop of evolving the inspiral, every, let's say, 10 revolutions, we calculate again the new fluxes, and we let it evolve to the next geodesic, and the next geodesics, and the next geodesics, until we have the plans. Actually, this is not a good, to use post-Newtonian means that it's not good to plans, okay? We go up to periastron 5M. After that, the accuracy is lost. But the accuracy, let me finish, is Babat here, and of course all the others that worked on this problem, compared Topolsky-based waveforms with a adiabatic approximation plus numerical class for generic orbits, and they found 95% matching, which is very good. So they thought, okay, this thing works, we can do phenomenology.
There are reason why like 10 orbit before dating and 5, why not one?
You can do as you wish.
That's one.
Yeah. It depends on your computational, resources.
But did you do some convergent tests by changing the number of orbits before the
Yes,
update?
yes, the change is extremely small in the fluxes. It's like order. I used in my code, I used 5 revolutions, and it took like a lot of time to finish the inspiral that I wanted. And then I used 1,000. Actually, not even. I didn't even do any updates. I just used a linear approximation of the flux. The initial energy plus the flux times time. And the difference was less than order 10 to the minus 6. I mean, maybe here it's important, but that's why I'm saying that we're doing phenomenology with these systems. Other people try to do parameter estimation, but they are doing it with less approximation. But here is where we stop. And now we have the methodology to evolve EMRIs.
So what exactly do you mean when you say dam?
Done. I mean, you start with a geodesic. You calculate its orbital elements. The fluxes depend on the orbital elements, eccentricity, semi-lattice rectum, inclination. You calculate the fluxes. I use this linear approximation for some geodesics, and they evolve with time, so they jump from geodesic to geodesic. And then I stop at some point and I say, okay, let's recalculate now again the new eccentricity, new semi-lattice rectum, new inclination, new fluxes. So I augment the fluxes in every loop so that it's not a linear evolution, but essentially a non-linear one. Like I put second order terms.
So basically what you say, the stamping is the particles dissipate energy.
Yeah. Energy, angular momentum, and the Carter constant.
The stamping is a little bit.
Yeah, I know. Let's say success in geodesics. I don't know how to call it. Anyways, so now I'm gonna stay here at the geodesic level first. This black line that last time I said is just a black line. It's the curve of zero velocity. This is where the turning points of any generic orbit stops. So if I give correct initial conditions, I will have a box here in this r theta plane because we care about r and theta. T dot, phi dot, we can evolve as we wish, or plug in T dot and work with respect to coordinate time instead of proper time. Yes.
But so if you have separability, it will fill the rectangular box because of the decoupling of the theta and r motion, whereas if it's chaotic, it will fill the whole cavity, right?
Oh, it fills the whole cavity either way. A chaotic orbit does exactly the same thing as a generic orbit. The difference is that it has dependence on initial condition, very delicate dependence. It's transitive between some periodic points, stable or unstable, it doesn't matter. And it's dense, but a normal generic orbit can also be dense. So if I evolve this for a long time, it will give me a box.
Yeah,
If
but
I-
the chaotic orbit it will not be rectangular. No? It will.
No, as far as I've checked, I mean, make similar boxes, and I mean, it doesn't behave erratically. It behaves erratically if you compare two different orbits that are very close, and you calculate the difference, the phase of these two orbits. At some point, it's gonna start going like this. So this corresponds to a generic orbit that has a ratio of the periastron-Laplacian frequency and the polar frequency theta plus theta minus. And this ratio is irrational. Okay, it's not a rational number. And that's why we start from some point, I think, here. And we never go back to this point. We feel the torus that the orbit leaves densely. If we're lucky enough, we can hit a resonance, as this one, which starts from one point, does some revolutions, go back to the same point. And you see that it goes from 14M to 5M. It's like a large difference. And if you do that many times, then you affect the shape of the orbit. And this is what gravitational self-force captures. If you have the resonant effects that I took away, I throw them away. And the resonant orbit has a ratio that is rational. So it's, let's see, this is the GIF that was not playing last time. It basically shows an r theta orbit. This is the 2/3, but doesn't show anything special here in the XYZ pseudo-Euclidean, let's say, coordinates. So if you see a generic orbit, it will also do something like this. But this orbit is special. So you have to see it in the phase space and understand what is happening. So, as I said, if we have this rational ratio of these two frequencies, and they are plenty, till we reach the ISCO and then plunge, then we can see what is called a resonant kick in the fluxes. So the fluxes suddenly realize that there's something else besides dissipation. And if we take this into account, it gives extra contributions to the phase, and the fluxes jump. And in EMRIs, we expect a lot of these resonances to be crossed, especially the 2/3, which is the most, let's say, the strongest one in EMRIs, because simply, I mean, it passes twice in the strong field regime, as it does 3 theta plus theta minus oscillation, and by doing that, it affects more the kick. It's a very special one, a very special resonance, because it also is very usual to EMRIs. This resonance usually occurs in intermediate eccentricity, not too much, not too little eccentricity, okay? Moderate eccentricity. And this we can hit at some point with some EMRI. So let's see this resonant kick. Now, this is the problem here in hand that we need to focus on. The blue oscillation is the evolution of the flux of energy in Kerr with respect to time. The resonance is hitting right at 0. They have put it there, centered it, and you see what is called a resonant kick. So this blue thing is gravitational self-force. Okay, it's evolution of the fluxes pure gravitational self-force. We have the resonant effects in. Now, if we take them out, as I said I would, we can only do the adiabatic approximation, which is straight lines. If we start from here and fit, we see that the straight line goes up, the fluxes go up. Doesn't really make sense. This one may be somehow better, but the best fit you can do, I think, is these two here with the adiabatic approximation. These dashed lines correspond to no resonant effect. So if we don't include the resonant effect, we don't see anything here. But what we want to see is the red line, the red dashed line. That's what we want. Not as a step, something more smooth, but initially it can be a step. It can be a step function. Now, people, I don't want to say people are lazy. I want to say people are smart. They don't, if you don't want to deal with self-force, which is really hard, you try and try and try for many years to find different methods to make this happen without caring about extremely intricate analytical calculations. And the first people that did that was in 2021, Lorenzo Sperry and Jonathan Gere. So they take the leading order dissipative component, which is insufficient to see resonances, these numerical clutch fluxes that I explained, and they add an effective resonance modeling on it. So another approximation. Again, phenomenology. I write this as ERM. This simulates the resonant contribution to the fluxes through an impulse function. An impulse function is very typical for signal processing. It's this WT. So you see now that the fluxes with respect to coordinate time are the numerical clutch fluxes that we know, Gaia and Labadakis, plus the resonant coefficient and this W. So for each E, L, Z, and Q, we have CE, CLZ, CQ. They have different coefficients, which people have sat down in care and found them. And they have made large tables, and we are using them. But first, Lorenzo and Jonathan did that. And this is the impulse function. So from start plus T start, from T start, comma T start plus the time of the resonance, you enable this function, which is again one of the many impulse functions. They chose one. There are plenty. This is not like a very specific model that they made by hand to make sense. Okay, and the resonance duration we can find with this equation that comes from the resonance condition. Now, if you want, we can discuss this later because I don't see that I have much time on how to get here. But now we have also a term that understands when we're crossing a resonance, because there's a resonance condition and it tells us we are close to a resonance. What do you want to do? Turn this on or not? Lorenzo Sperry and Jonathan Gere did this for the strongest resonance, the 2/3. And here we reproduced two waveforms, one with numerical clutch, one with numerical clutch plus the effective resonance model. What we see in the first one, which is an EMRI with a steam 0.8 and some initial parameters, is that there is a dephasing, right? But other than that, the amplitude is not that much affected. If we calculate the mismatch between these two waveforms that last around 10 days, it's 0.24. Okay, mismatch is 1 minus overlap, 1 minus match. So the larger it is, the more dephasing we have. This one that looks better by naked eye runs for almost a year. And we see that if we calculate the mismatch, it's almost 1, 0.99. Why? Because the dephasing grows with time.
But I was wondering, like, I would have thought, like, in these plots, where does the resonance start, right? Where's the T start?
Yeah, don't worry. You're not gonna see anything at the waveform level. That's the thing.
No, but if the dephasing is going to happen between these two models, wouldn't
No,
you
no.
expect that sort of the waveform match, and then when the resonance starts, then they start dephasing or something like that?
Yes, yes. So we have chosen semi-lattice rectum, which essentially chooses the initial conditions, the initial position of the EMRI, to be close enough to cross a resonance, the 2/3. And then we let the dephasing evolve, right? We let this waveform evolve, and then we calculate the mismatch, which is the dephasing. So the resonance is met at the beginning, almost at the beginning of the inspiral. So we see the maximized mismatch. This is just for the 2/3. But why only the 2/3? I explained why, and this is fine. But what happens when we take into account subdominant resonances? Does something change? So again, we choose some initial conditions, and we involve some EMRIs, different cases, and we plot the fluxes of energy angular momentum and Carter constant. And the gray part is only crossing the 3/2 or the 2/3 resonance, which is, as you see in the beginning. So we see a big jump in the Carter constant. The gray line here is overlapping with the blue one. So we see a jump. We see two more jumps on these ones, the energy and LZ. This is what the work of Sperry and Gare took into account, and the deep parameter estimation. We evolved more. We found another resonance, 2/1, in the same inspiral. It doesn't look like it gives a particular, like a strong jump on Q. It does, but not strong enough. But LZ now gains a large kick. On the last, so we go from right to left because this is the inspiral. T is becoming slower because it's a semi-lattice ray. And at the end, we also make the 3/1 resonance. We use particular coefficients for every kick now. So we enable the impulse function 3 times because the EMRI crosses these 3 resonances, the one that we found. And you see the difference. The gray lines, the maximum they can get is up to 0.75. But surprisingly, DLZ can reach up to 1.25 times 10 to the minus 2. So the fluxes are really changing even for subdominant resonances. And this is what we took into account. And how does this affect, let's say, some of the orbital elements? Here I have the difference. Okay, the difference of inclination minus the inclination if we don't take into account resonances at all. So it's like the adiabatic. And I plot in gray only the contribution again of the 3/2. And you see that we have the same jump. And then it stops here where we have the plants. Now we have time from left to right. And if we take these 3 resonances all together, we see a different evolution, a very large jump actually in 2/1, and another very small one at 3/1. We're very close to plants, things close to the ISCO. Let's say things evolve very fast. That's why we don't see too much here, but here it's extremely obvious that we have different evolutions here. So by calculating the orbital dephasing of 4 different static cases with large eccentricity, with small eccentricity, large inclination, small inclination, and semi-lattice rectum chosen so that we start close to the 3/2 resonance, we have a lot of data here, but I want you to focus on the varying C, which means that we use different coefficients for the different fluxes that we augment with the resonance model, because at the paper of Lorenzo Sperry, the coefficient is the same for all constants of motion, let's say. So they find the maximum from a paper from Hinderer and Flanagan, which is 0.01, and they use this one for energy, LZ, and Q, even though the maximum is only at the Carter constant. But we play around with this knowledge that we have from papers, from other papers. And if you see this box, which is a contribution of 3/2, 2/1, plus 3/1, you will see an orbit that it always dominates the orbital dephasing. This box is for these 4 cases, which lie on this line. These lines don't mean anything, right? We just have 4 different cases. The box is always the highest because it has contributions from the resonance. Finally, and I think I will stop here, even though I want to talk about chaos a little bit, but that's fine. We calculate the gravitational wave mismatch as we did before, but now it's a more delicate one because it takes into account more resonances. Again, look at the boxes and the rhombus or crooked square box, whatever. they all lie on top of the mismatch. In fact, we have chosen a signal to noise ratio equal to 30. So the distinguishability mismatch is 10 to the minus 3, which we have here. So almost all of the contributions of different resonances or combined resonances lead to a gravitational wave mismatch that is detectable by laser. And if we put all of them together, then this is maximized close to 1. Which means that the overlap is essentially 0. So I think, yeah, I'll stop here because I spoke a little bit about chaos the other time. So that's it. Thank you very much.
I wonder if another form of this impulse function has been tried.
No, not yet. As you saw, this paper is 2021, and we at 2025 used this model to add more resonances. People should play in general with impulse functions, but it really depends on initial conditions, where you start your orbit, because now we start in a very nice position that we cross one resonance at least. If you do this in a much more generic way, it's going to be much harder to predict which impulse function is best for its resonance and for its initial conditions. You have to stick with one and play with it. That's something that somebody can do, but yeah, different impulse function. I would expect qualitatively similar results. That's it. Quantitative, I'm not talking about quantities here. I'm not allowed. Too many approximations.
Anyway, you want to get very precise waveform, right? So
Yeah.
So coming to that, actually, I have another question, which is like, is there a way sort of to validate that impulse function is a good approximation? But like you compare to some other way to compute the waveform or the fluxes, right? So start from more first principles or something. Is there a way, or is
Yes,
no,
but
no,
again, for specific orbits. So they have done some fitting on the fluxes that have been found with gravitational self force for a specific case from a specific paper, and they found that this impulse function matches better the jump of the energy and the others. But again, you need to have gravitational self force data to fit them in order to make impulse functions. So it should work the other way around. We should use the easy way to understand the hard way. But here, we depend on the hard part. You know, we depend on self force. We cannot, for example, say, okay, now I'm gonna deform my space-time, I'm gonna break symmetries, I'm gonna do whatever I want, and I will use the same coefficients, for example, or of resonances. We don't know them. These come from gravitational self force. So there's all that is for Kerr, okay? And specific initial conditions, specific times that it runs, and we see how large is this coefficient, how much it keeps. These are the maximized ones, the bold ones, for its case, for its scene. So we don't know. For other theories of gravity, we need to redo self force. But as Nicola said, if we know that the contributions of a modified theory of gravity go beyond second order, then it's safe to use this value, I think. Actually, if you know a theory that
what I was saying was modified effect actually fits in the adiabatic order, then to want to detect it, you don't need to model like every order. You just say like a interpretation effect and every.
Yeah, but then how are you gonna characterize it?
No, I mean, you
Yeah.
need to be able to.
The
characterize
detection,
it if
okay,
you
I mean,
detect
if we have, if we break in the Carter constant, we get this huge jump here. There's no reason to calculate mismatch. We can see it in the waveform, you know, because we're crossing some weird region of the phase space of the orbit that we have a resonant island. So it's not a resonance that is one point and we cross it sometimes. We are crossing it for a week. We are in resonance for a week. This creates this modulation in the frequency domain. It's this plateau. So, I mean, yes. This is at the abatic. That's the thing. This is at the abatic level. Somehow, because we prolong this the stay in this resonance, the resonant contributions are sourced in the diabatic level. I don't know how. I mean, it's we never expected to see anything, to be honest, when we did this work. That's why it's fascinating, because there's no resonant effects taken into account. If you take into account resonant effects, this will be even larger, this jump. This is one of the frequencies, right? The fundamental one. We did the Fourier transform, we also found from the waveform and so on and so forth. And if you have a Carter constant, you don't see anything. Do I have it? Yes. No. That then. Here, this is a deformed pair. It's not pair. We have had some deformation. Straight line. And we cross the resonance around the same time. I mean, you have to zoom in, right? And see if there's something happening in this band. But to do this in a spectrogram is really, really, really hard, because there's an uncertainty principle. The more you look at the frequency, the more you lose the time accuracy, and vice versa, because you take boxes and you move them to do the Fourier transforms. And it depends that if you want to keep the volume constant, then when you make it smaller, this will become bigger. So ambiguity in frequency, but better time, you know, and vice versa again.
If you enjoyed the video, like and subscribe.